Okay, so in this last section, we're going to look at two problems. So the first problem is if you have a curve, or not a curve, but a lamina, that's the region under a curve. So say if I draw some kind of a curve here, something like this, y is equal to f of x, and consider the lamina formed like this, say between 2 points A and B. Now, when I say lamina, a lamina is a 3D object, but it's very, very thin, and so you can essentially treat it like a 2D object. So there's some very, very, it's got a very, very small thickness here. So kind of metal sheets or stuff like this. So you can kind of treat them, even though they're actually three-dimensional objects, you can treat them essentially like two-dimensional objects. Something like this. Okay, so you got this kind of sheet in this shape. The first thing which we should know by now is that the area is given by the integral from a to b, and the next question that we're looking at here is what are the coordinates of the centroid. Now I think I'm making some assumptions here. So a centroid is like kind of the position of the average x coordinate and the average y coordinate, essentially, divided by the area as such. But what I'm going to assume for us is that we're going to assume uniform density. And if you assume uniform density, so it's not denser on the edges, then the centroid is the same as the center of gravity. Okay, so the center of gravity will be a place where you can, if you cut out this piece, that you could balance it on your finger. So maybe it's somewhere like this. X bar, Y bar. Now I think in the appendix to this section, I derived these formulas below, but in an assessment situation, these formulas will be given to you. So it turns out that the x coordinate of the centroid, or the center of gravity, is the integral from a to b of x by y, where y is this curve, divided by the integral of y. And of course the integral of y is nothing but the area. The y coordinate is slightly more complicated. It's half the integral of the y squared divided by the area. If you want to see where these formulas come from, you can find this appendix. Usually you will have found the area in a previous part of the question. Okay, so I think I have an example here, or two. Let's see. Okay, so the question starts here. Determine the area between the curve y equal to 2x squared plus 3, the x-axis, and the ordinates x equal to 0 and x equal to 3. Okay. Now, what the question will usually do, it'll kind of break down, and first it'll ask you to sketch it. There's various different ways of sketching this 2x squared plus 3. One of them is knowing that it looks like a U quadratic. But what I'm probably going to recommend that we do is actually that we plot points. Now plotting points is kind of, it's not really the way to be doing things, but if you don't know, you see, you have to know quite a lot about the different curves to be able to, like I can do a rough sketch, I know what this thing looks like before I do it, but if you don't, and maybe a lot of us don't, we should plot points. So we're looking between x equal to 0 and x equal to 3, so we'll plot 4 points. So x, y. So x equal to 0, x equal to 1, x equal to 2, and x equal to 3. So if I put 0 into the 2x squared plus 3, I get out 3. If I put, so this is kind of relationship between the y coordinate and the x coordinate. So if I put x equal to 1 into this, I get out 5. If I put x equal to 2 into this, I seem to, what do I get? Do I get 11? And if I put x equal to 3 into this, I get 21. Okay. So we're only going to be really interested in a rough sketch here. So we'll do it quite roughly. If I can get some nice units. In terms of your assessment here, you won't have necessarily have access to graph paper. You can do this roughly, it's fine. But if you want to get some graph paper in your next shop or whatever, it might make this question a bit easier when it comes to that time. Okay, so anyway, we'll do, let's say, 5, 10, 15, 20, something like that. This only has to be rough. And then we need to go up to x equal to 3. So let's go with 0, 1, 2, 3. And so we get something like, okay, x equal to 0, y equal to 3. It only has to be a rough thing. It's perfectly okay. Say there. X equal to 1, y equal to 5. X equal to 2, y equal to 11, something like this. And finally, x equal to 3, y equal to 21, something like this. Yeah, this is absolutely fine. And then join the dots up in a smooth way. Okay. So it would ask you to sketch this. So it's this is the curve. Then you've got the x-axis and the ordinates x equal to 0 and x equal to 3. We're looking at this kind of shape here. Now that's kind of gone over the edge a bit, but sure bad. So this now is a lamina that we're considering. Okay. So so that'll be the first question, sketch it. That's a perfectly good sketch. It can be rougher than that. I do like labels on axis, but that's perfectly good. Next question then will be, what's the area? So you find the area by integrating the function 2x squared plus 3 between 0 and 3. So the area is equal to the integral from 0 to 3 of y, which is 2x squared plus 3. Now you can get a requirement for integration by parts in here. Just something to look out for. But this one, okay, we've got our strategy, we've got an integral, we need to anti-differentiate. What's good is it's a sum, so we can do term by term, fixing constants, and what's good is both of these are in the tables. This is a direct, this is an easy one. So we can anti-differentiate straight away. Fix the 2, what is the antiderivative of x squared is x cubed over 3, and then have a think, what do I have to differentiate with respect to x to end up with 3? It would be 3x. Remember, of course, we can pause this video at any time. And now you do top limit minus bottom limit. So you get, say, 2 x cubed over 3 plus 3 times, substitute in top limit. The top limit here is 3. Minus substitute in bottom limit. Now, one of the things is if you think that a 0 always gives you a 0, that's not correct. For example, if there's a cos x, cos of 0 is 1, or an exponential e to the 0 is 1. So you have to be a little bit careful. But if it's powers of x, the 0 will give you zeros. But we'll just be a little bit careful. Top limit minus bottom limit. So 0 cubed, this thing is equal to 0. And now this thing on the left-hand side is 2 by 9 plus 9. It turns out to be 27. It's probably worth kind of checking our answer, because you can estimate the area of this kind of, you can overestimate it maybe using the rectangle and a kind of a triangle. So this is something I've kind of been looking at. If you have a picture in front of you, you can kind of check your answer. So the area of this bit is equal to 3 by the height is 3, that's equal to 9. And then this will be, the area of this will be bigger than, now I've included the equals, which is ridiculous. This area is certainly less than the area of the triangle, which would be half the base, which is 3, and then the height is 21 minus 3, which is 18. And that would give you 27. So as it happens, actually, this area above here equals this area under here, because the total area is 27. So actually this area is equal to 18. Okay, that's not too important. Just messing around, understanding that the integral is the area, and if you have a picture in front of you, you can estimate the area. No marks for that, but it's just a bit of maths. Okay, second thing, determine the centroid of this region. And of course, what's good here is you'll want your answer to make sense. Your center of gravity shouldn't be up here, over here, down here, or anything like that. It should be, now it can happen that it isn't inside the interior of the shape. Now we are working in 2 dimensions here, like so. It can happen, like for example, if you think about a toilet seat, the centroid of a toilet seat isn't actually, you can't actually hold up the toilet seat. That can happen, but you won't get the centroid here, here, up here, or over here. Okay, so if we're asked to get the centroid, what we have to do is calculate a few integrals, 3 of them in fact. The bottom one we've already done, the integral of y. So this would be on the exam question, the formula. The integral of y we've already found is 27. So let's look at the integral of x by y first. Okay, so the integral of x by y, we're integrating from 0 to 3, x by, and y is 2x squared plus 3. Now written like this is a little bit dodgy because it kind of messes up BAMDAS. You should put a bracket there. Okay, now we're confronted with an integral. Now you can, if you're a bit daft, for example, go at this with integration by parts, but that is completely daft. First you go doing it with the tables. Now the tables will say, well, hang on a minute, they're multiplied together, so I can't do it term by term, so I can't do the tables straight away. So what you're going to have to do then is the next strategy is a manipulation, and sure enough you can multiply this out. You can go on to substitution, but I'm trying to recommend, if possible, that you go for the easiest possible thing, the first thing on that list of tables, manipulation, substitution, parts. And manipulation is more basic than substitution. So just do the manipulation, multiply this out. So x by 2x squared gives you 2x cubed, and x by 3 gives you 3x. And now this can be done directly using the tables, because you can, it's a sum, you can do term by term, fixing the constants. So off we go, fix the 2. And the antiderivative of x cubed is x to the 4 divided by 4, plus fix the 3, and now recognize that x is x to the 1, and so its antiderivative is x squared over 2. And you're going from 0 to 3. So now you do top limit minus bottom limit. So we're talking 2, 3 to the 4 over 4, plus 3 to the 2 over 2, that's substitute top limit, we'll do it in a minute, minus substitute bottom limit. Again, there's a 0, but I'm going to be careful. So 2, 0 to the 4 over 4, plus 3, 0 squared over 2. Substitute top limit, minus substitute bottom limit. This just gives you 0. I think I'm going to go into the calculator for the rest of it. So I get 2 by 3 to the 4 divided by 4 plus 27 over 2. And it gives me 54. And now the formula for x bar is the integral of xy over the integral of y. Oh, there's one small remark here I'd make. There's no simplification here. You have to calculate them separately, and I wouldn't calculate them at the same time. I would calculate them separately, and in fairness, usually the bottom will be calculated in a previous section. So the integral of x by y we just found is 54. The integral of y is 27. So the x coordinate of the centroid is 2. So there's going to be a last part to this where you indicate on your sketch the position of the centroid. It's going to be along this line here, x equal to 2. Okay, now we need to find the y-coordinate. So for the y-coordinate, we're looking at half the integral of y squared, so let's find the integral of y squared. Okay, so this is the integral from the integral of y squared 0 to 3, and y is 2x squared plus 3. Of course, that 2x squared plus 3 will change for different questions, dx. Okay, now what we should do here is first we try and go in the tables. Now you can get into big trouble with the tables here because it's inside the square, it's not actually a sum. So you cannot do this directly from the tables. You should try manipulation, and you should be thinking about multiplying out. So we'll do 2x squared plus 3 by 2x squared plus 3, see what we get, and that should be no problem. So 2x squared by 2x squared is 4x to the 4. 2x squared by 3 is 6x squared. 3 by 2x squared is 6x squared, and 3 by 3 is 9. And so we get 4x to the 4 plus, remember you can pause this whenever you need to, plus 12x squared plus 9. So we can manipulate, we can rewrite the thing we're integrating as this. Now we anti-differentiate, run out of space here, we'll throw it here. So it's a sum, so there's no squaring here, there's a sum, so you can do term by term, fixing constant. So fix the 4, antiderivative x to the 4 is x to the 5 over 5, plus fix the 12, antiderivative x squared is x cubed over 3, and think about what is the antiderivative of 9. What do you differentiate with respect to x to end up with 9? It would be 9x. And now you do your top limit minus bottom limit, so you would get 4 3 to the 5 over 5 plus 12 3 to the 3 over 3 plus 9 times 3. Take away, that's going to be the substitute, the top limit, then the bottom limit. 4 times 0 to the 5 over 5 plus 12 times 0 cubed over 3 plus 9 times 0. Now if you're being careful, you can just write 0 here because 0 to the 5 is 0, 0 cubed is 0, 9 by 0 is 0. If you want to be a bit quicker, you can be quicker there. So that's 3, 3, 3, substitute top limit, 0, 0, 0, substitute bottom limit. And we'll bang this into the calculator as well. So I get 4 by 3 to the 5 divided by 5 plus 12 by 27 over 3 plus 27. And I'm getting 1647 over 5 because it's fixed because it's fifths. There's no rounding involved. That's good. And so we get that y bar is equal to half the integral of y squared dx, which we just found, divided by the integral of y dx, which we found earlier was the area, was 27. You get half 1647 over 5, that integral, divided by 27. So I'll bang this into the calculator, and I get 61 over 10, which, because we're going to sketch it, we'll write in decimals as 6.1. So we have that x bar, y bar is equal to the x coordinate is 2 and the y coordinate is 6.1. So let's go back to our sketch. Across the 6.1, something maybe like this. And so this is the centroid. Now, one of the reasons you might be looking at this is it's just some theoretical understanding that if you are looking for the centroid of, say, a rectangular plate or a circle or anything like that, and you look it up, you Google it or whatever, and you get a formula, the question is, where does the formula come from? And the formula comes from doing integration. This is the big reason you're looking at this here.